Welcome to this lesson on one of the most fascinating paradoxes in semiconductor physics, how shrinking bulk silicon can transform it from a dark, inefficient light emitter into a bright, luminescent material. The paradox is this: bulk silicon is an indirect bandgap semiconductor and a terrible light emitter. But when you shrink silicon down to the nanoscale, creating silicon nanocrystals, it can suddenly emit light efficiently. How can simply changing the size turn a dark material into a bright one? To understand this paradox, we first need to understand what band structure means and the difference between direct and indirect bandgaps. In solid materials, electrons don't have discrete energy levels like in atoms. Instead, they occupy continuous bands of allowed energies. The valence band is where electrons normally reside at low temperatures. It's the highest occupied band. The conduction band is above the valence band. When electrons reach this band, they can move freely and conduct electricity. The band gap is the energy difference between the top of the valence band and the bottom of the conduction band. It's a forbidden energy region where no electron states exist. Here's a simplified energy diagram. The conduction band is at the top, the valence band at the bottom, and the band gap separates them. Mathematically, the bandgap energy, Eg, equals Ec minus Ev, where Ec is the conduction band minimum and Ev is the valence band maximum. Now here's the crucial distinction: direct versus indirect bandgap. In a direct bandgap semiconductor, the minimum of the conduction band and the maximum of the valence band occur at the same crystal momentum, or K value. Electrons can transition vertically in K space. In an indirect bandgap semiconductor, the conduction band minimum and valence band maximum occur at different K values. An electron transition requires a change in momentum. On the left is a direct gap where the transition is vertical. On the right is an indirect gap where the transition is diagonal, requiring a momentum change. You might ask, why does this difference matter for light emission? The answer lies in momentum conservation. Photons, the particles of light, carry energy but very little momentum. The momentum of a photon is h bar times k photon, where k photon is very small for visible light. The photon momentum equals h bar k photon, which also equals h divided by lambda, where lambda is the wavelength. For visible light with wavelength around 500 nanometers, the photon momentum is about 10 to the minus 27 kilogram meters per second. This is negligible compared to electron momentum in crystals. In a direct gap semiconductor, an electron drops from conduction band to valence band at the same K value. The tiny photon momentum is enough to conserve momentum, so photon emission is efficient. In an indirect gap semiconductor, the electron must change its crystal momentum significantly. A photon alone cannot provide this momentum change. The electron must also interact with a phonon, which is a lattice vibration. The change in electron momentum delta K electron must equal the phonon momentum K phonon to conserve total momentum. This makes indirect transitions a three-particle process. Electron, photon, and phonon must all interact simultaneously. This is much less probable than a two-particle process, making indirect gap materials poor light emitters. Silicon is the classic example of an indirect bandgap semiconductor. Let's look at its properties. Silicon has a bandgap of 1.12 electron volts at room temperature, corresponding to infrared wavelengths around 1100 nanometers. In silicon's band structure, the valence band maximum occurs at the gamma point, where K equals 0, but the conduction band minimum occurs at about 85% of the way toward the X point in the Brillouin zone. The momentum difference is approximately 0.85 times 2 pi divided by A, where A is the silicon lattice constant of 5.43 angstroms. Because of the indirect gap, the radiative recombination time in bulk silicon is on the order of milliseconds. This is extremely slow compared to direct gap materials. The internal quantum efficiency for light emission in bulk silicon is typically less than 0.001%. This means fewer than 1 in 100,000 electron-hole pairs produce a photon. Now we arrive at the key to solving the paradox: quantum confinement effects in silicon nanocrystals. What happens when we shrink silicon down to the nanoscale, creating particles just a few nanometers in size? The answer involves quantum mechanics. The Heisenberg uncertainty principle tells us that confining a particle in space leads to uncertainty in its momentum. Delta x times delta p is greater than or equal to h bar over 2. This is the mathematical statement of the uncertainty principle. Delta x is the position uncertainty, and delta p is the momentum uncertainty. When we confine electrons to a nanocrystal of size L, the position uncertainty is approximately L. This means the momentum uncertainty increases as we make L smaller. The momentum uncertainty is approximately h bar divided by L. As L decreases, delta P increases. In terms of crystal momentum, this creates an uncertainty in k-space. Delta K is approximately 1 over L. The k-space uncertainty, delta K, is approximately 1 over L. For a nanocrystal of 3 nanometers, this is about 0.3 inverse nanometers. Here's the key insight. When the k-space uncertainty becomes comparable to the indirect gap momentum difference, the concept of crystal momentum becomes ill-defined. The electron wave function in the nanocrystal is no longer a pure block state with well-defined k. Instead, it's a superposition of many k-states spread over a range delta k. In bulk silicon, electrons have sharp k values shown by the single arrow. In a nanocrystal, the k values are spread out over a range, shown by multiple arrows in different directions. This spreading of k values has a profound consequence. It relaxes the momentum selection rules for optical transitions. Because the electron state now has components at many different k values, including near the gamma point, the transition probability for photon emission increases dramatically. Even though the band structure itself hasn't changed, the confined electrons can now undergo what appear to be direct transitions. These are sometimes called pseudo-direct transitions. The radiative lifetime tau rad becomes size-dependent, scaling approximately as L to the power of negative alpha, where alpha is between 1 and 2. For silicon nanocrystals around 3 nanometers in diameter, the radiative lifetime drops from milliseconds to nanoseconds. That's an improvement of about 6 orders of magnitude. The internal quantum efficiency can increase from less than 0.001% to over 60% in well-passivated silicon nanocrystals. This is a truly remarkable transformation. Quantum confinement doesn't just affect momentum, it also changes the energy levels, further enhancing light emission. In a nanocrystal, the continuous energy bands break up into discrete energy levels, similar to atoms. The smaller the crystal, the more widely spaced these levels become. For a particle in a box model, the energy level scale is n squared divided by L squared, where m star is the effective mass and n is a quantum number. The effective band gap increases as the nanocrystal size decreases. This blue shifts the emission wavelength from infrared toward visible light. The effective band gap equals the bulk band gap plus a confinement term that includes the electron and hole effective masses. This term grows as 1 over L squared. Let's do a numerical estimate. For a silicon nanocrystal with diameter L equals 3 nanometers, we can calculate the confinement energy. The electron effective mass is about 0.26 times the free electron mass, and the hole effective mass is about 0.39 times the free electron mass. Plugging in the numbers, the confinement energy is approximately 0.6 electron volts. This shifts the emission from 1100 nanometers infrared to about 700 nanometers red light. By controlling the nanocrystal size, we can tune the emission color across the entire visible spectrum. Smaller crystals emit blue light, larger ones emit red light. Here's a visual representation showing how different nanocrystal sizes emit different colors, from blue for the smallest to red for the largest. There's another critical factor that determines whether silicon nanocrystals will emit light: surface passivation. Silicon nanocrystals have an enormous surface-to-volume ratio. Surface defects create trap states in the bandgap that capture electrons and holes, leading to non-radiative recombination. Dangling bonds at the silicon surface are the main culprit. Each surface silicon atom can have one or more unsatisfied bonds that create deep trap states. To achieve bright luminescence, the surface must be passivated, typically with hydrogen or oxygen. This removes the dangling bonds and eliminates the trap states. The quantum efficiency equals the non-radiative lifetime divided by the sum of radiative and non-radiative lifetimes. Good passivation makes tau and R very long, approaching 100% efficiency. Now let's look at experimental evidence for this remarkable transformation from dark to bright silicon. In 1990, Lee Canham discovered that porous silicon, which contains silicon nanostructures, emits bright visible light. This was completely unexpected for an indirect gap material. Modern silicon nanocrystals with proper passivation can achieve photoluminescence quantum yields exceeding 60%. This compares to less than 0.001% for bulk silicon. Time-resolved photoluminescence measurements show radiative lifetimes decreasing from milliseconds to microseconds to nanoseconds as crystal size decreases, confirming quantum confinement theory. Experimental emission spectra show clear size-dependent shifts, with smaller nanocrystals emitting at shorter wavelengths, exactly as predicted by quantum confinement models. Let's make this more rigorous with the mathematical framework used to describe quantum confinement. We model the electron in whole using the effective mass approximation, which treats them as particles with effective masses moving in a confining potential. For the electron, the Schrödinger equation involves the effective mass me star, the confining potential Ve, and the wave function psi e. Similarly, for the whole with effective mass mh star, the total energy is the sum of electron and hole energies plus their Coulomb interaction. For a spherical nanocrystal, we often use an infinite potential well approximation, where the potential is 0 inside radius r and infinite outside. The solutions are products of radial functions r and l and spherical harmonics ylm, characterized by quantum numbers n, l, and m. The energy levels are ENL equals h bar squared times xnl squared divided by 2 meter star r squared, where x and l are the zeros of spherical Bessel functions. The lowest energy states are labeled 1s, 1p, 1d, similar to atomic orbitals. The 1s to 1s transition is typically the brightest. We haven't yet discussed the Coulomb interaction between the electron and hole, which creates what we call an exciton. An exciton is a bound state of an electron and hole held together by Coulomb attraction. It's like a hydrogen atom, but with much weaker binding in bulk semiconductors. The Coulomb energy is negative E squared divided by 8 pi epsilon 0 r, where epsilon is the dielectric constant and r is the separation. In bulk silicon, the exciton Bohr radius is about 4.9 nanometers. This is the natural size of the electron-hole pair. When the nanocrystal is smaller than the exciton radius, we're in the strong confinement regime. The confinement energy dominates over the Coulomb energy. In strong confinement, the exciton binding energy actually increases, scaling as 1 over L. This further stabilizes the excited state. The confinement also increases the oscillator strength, which is the probability of optical transitions. The electron and hole wave functions overlap more strongly in a confined space. It's instructive to compare silicon nanocrystals with naturally direct gap materials like gallium arsenide or cadmium selenide. Gallium arsenide has a direct band gap at 1.42 electron volts, with radiative lifetimes of nanoseconds even in bulk form. Cadmium selenide quantum dots are already bright emitters because the bulk material is direct gap. Quantum confinement just tunes the color. Silicon nanocrystals are unique because they transform from fundamentally dark to bright. This is the essence of the paradox we're exploring. The advantage of silicon nanocrystals is that silicon is abundant, non-toxic, and compatible with existing silicon technology, unlike cadmium-based quantum dots. This transformation from dark to bright silicon has profound technological implications. Silicon nanocrystals could enable silicon-based light sources for integrated photonics, allowing optical communication on silicon chips. They're being explored for LEDs and display applications, offering a potentially cheaper and less toxic alternative to other quantum dots. The biocompatibility of silicon makes these nanocrystals attractive for biological imaging and sensing applications. Interestingly, quantum confinement in silicon can also enhance solar cell efficiency through hot carrier effects and multiple exciton generation. Despite decades of research, some fundamental questions about the indirect-to-direct transition remain open. One question is, what exactly is the critical size where silicon becomes bright? Is there a sharp threshold, or a gradual transition? The answer appears to be a gradual transition. Above 5 nanometers, silicon remains quite dark. Below 2 nanometers, it's consistently bright. In between is a transition region. Another question: can silicon nanocrystals ever reach 100% quantum efficiency like the best direct gap materials? The answer is probably no, because even in strong confinement, some indirect character remains. Also, smaller crystals have more surface area, making passivation increasingly difficult. A critical question for devices is, can we achieve efficient electrically pumped emission, not just photoluminescence? This is more challenging because electrical injection can lead to nanocrystal charging and Auger recombination, which are non-radiative processes that reduce efficiency. Let's briefly touch on some advanced topics that go beyond a simple quantum confinement picture. The surface of silicon nanocrystals isn't just passive. Surface states can actively participate in the optical transitions, creating new emission pathways. The chemical nature of surface ligands can dramatically affect optical properties. Organic ligands can inject electronic states into the gap or modify the local dielectric environment. Introducing dopant atoms into silicon nanocrystals can create new emission mechanisms. A single phosphorus atom in a 3 nanometer crystal can dramatically alter its properties. Coupling silicon nanocrystals to plasmonic metal nanoparticles can further enhance emission through local field enhancement and Purcell effects. Silicon nanocrystals are just one example of quantum confined systems. Let's compare them with related structures. Quantum wells confine carriers in only one dimension. They show some, but not all, of the effects we see in zero-dimensional nanocrystals. Quantum wires confine in 2 dimensions. The indirect-to-direct transition occurs, but less dramatically than in nanocrystals. Carbon quantum dots show similar indirect-to-direct transitions. Graphene edges and small graphene flakes exhibit bright luminescence, despite bulk graphene being non-luminescent. 2-dimensional materials, like molybdenum disulfide, show a different but related effect. Bulk is indirect, but monolayer becomes direct due to changed symmetry, not just confinement. The theoretical description of silicon nanocrystals remains an active area of debate. One debate concerns how valid the effective mass approximation is for nanocrystals smaller than 3 nanometers. At this size, atomistic effects become important. Many body effects like electron-electron correlation become increasingly important in small nanocrystals. These can't be captured by single particle models. Surface reconstruction at the atomic level can significantly alter electronic structure. Different facets and reconstruction patterns lead to different properties. In small nanocrystals, excited states can be multi-configurational, meaning the simple picture of one electron and one hole breaks down. Let's work through a detailed numerical example to make this concrete. We'll consider a silicon nanocrystal with diameter 3.5 nanometers, which is 35 angstroms, containing roughly 1,400 silicon atoms. The bulk silicon bandgap is 1.12 electron volts. We use effective masses of 0.2, 6 times m0 for electrons, and 0.3, 9 times m0 for holes. The electron confinement energy is h bar squared pi squared divided by 2 meters E star L squared, which gives 0.23 electron volts. The hole confinement energy is 0.15 electron volts, using the same formula with the hole mass. The Coulomb binding energy is approximately negative 0.12 electron volts. The factor 1.8 comes from integrating over the confined wave functions. The effective bandgap is 1.12 plus 0.23 plus 0.15 minus 0.12, which equals 1.38 electron volts. The emission wavelength is hc divided by Eg, which is 1240 divided by 1.38, giving 900 nanometers in the near infrared. For visible blue emission around 450 nanometers, corresponding to 2.76 electron volts, we would need nanocrystals smaller than about 2 nanometers. Now we can present the complete resolution of the indirect-to-direct bandgap paradox. First, understand that the bulk band structure and its indirect nature don't fundamentally change. The conduction minimum is still at the X-valley, not the gamma point. Quantum confinement creates uncertainty in crystal momentum, spreading the electron wave function across K-space. This K-mixing relaxes the momentum conservation selection rules, allowing optical transitions that would be forbidden in bulk. What emerges is a pseudo-direct character, where optical transitions become allowed without requiring phonon assistance. The size dependence provides continuous tunability. We can dial the properties from bulk-like indirect to quantum dot-like pseudo-direct simply by changing size. Finally, proper surface passivation is essential to eliminate competing non-radiative pathways and allow the radiative transitions to dominate. This diagram summarizes the transformation. We start with dark, indirect bulk silicon on the left. Simply by shrinking it to the nanoscale, shown on the right, we create a bright, efficient light emitter. Let me briefly mention the experimental techniques used to study and characterize silicon nanocrystals. Photoluminescence spectroscopy is the primary tool. We excite with UV or blue light and measure the emission spectrum to determine the bandgap and efficiency. Time-resolved photoluminescence uses pulsed excitation to measure radiative lifetimes directly, confirming the transition from millisecond to nanosecond timescales. Transmission electron microscopy allows direct visualization of individual nanocrystals and measurement of their size distributions. X-ray diffraction and Raman spectroscopy confirm the crystalline structure and can detect phonon confinement effects. Ultra-fast pump probe spectroscopy with femtosecond resolution reveals carrier dynamics in relaxation processes. Let's conclude by looking at future directions and remaining open questions in this field. A major goal is achieving electrically pumped lasing from silicon nanocrystals. This would enable all silicon lasers for integrated photonics. Better understanding of hot carrier dynamics could enable more efficient photovoltaics through reduced thermalization losses. Learning to control and exploit coupling between adjacent nanocrystals could lead to collective effects and enhanced transport. Hybrid systems combining silicon nanocrystals with 2D materials like graphene or transition metal dichalcogenides show promise for novel optoelectronic devices. Silicon nanocrystals might find applications in quantum information, as they can host long-lived spin states while enabling optical readout. Let me summarize how we've resolved the indirect-to-direct bandgap transition paradox. The key insight is that quantum mechanics at the nanoscale fundamentally alters the optical properties of materials. The Heisenberg uncertainty principle creates K-space uncertainty that relaxes the strict momentum conservation selection rules of bulk materials. Size provides a continuous tuning parameter, allowing us to transform silicon from fundamentally dark to remarkably bright. This is a beautiful demonstration of how quantum confinement gives us control over fundamental material properties that are fixed in the bulk. Silicon nanocrystals represent a practical realization of quantum dots in an abundant, non-toxic, technologically mature material system. The paradox teaches us both about fundamental physics, how quantum mechanics governs the nanoscale, and about engineering, how we can design materials with desired properties.